So in this video, I'm going to work on some example related to conditional probability. The first example is about rolling two dice. So you roll two dice and you have two different events. One event that's going to be the sum of the two dice add up to a number that is greater than or equal to 7, and another event that is the first die is greater than or equal to 3. And this scenario can be illustrated in the following pictures. Again, you roll two dice. The first die will give you a number that is greater than or equal to 3. So you have the scenario here dotted in blues. And another event that is the sum of the two dice is going to give you a number that is greater than or equal to 7. So the first die is 1, the second die is 6. So you got one outcome there. The first die is 2, the second die is 6 and 5. So you have two outcomes here. The first die is 3, and the second die is 4, 5, and 6. So you have three outcomes, so on and so forth. So you roll two dice, and you have two different events. So it's one event, and I'm going to note here, event F, is that the event that the first die is a number that is greater than or equal to 3. And the event E that the sum of the two die is greater than or equal to 7. So you want to know what is the probability of E given F. So this is equal to the probability of E and F divided by the probability of F. So again, what we are looking for is we look for the probability of getting the sum of the two die to be greater than or equal to 7, given that the first die give you a number that is greater than or equal to 3. And that is equal to the probability of a number is greater than or equal to 3. That is equal to the probability of getting the number that is greater than or equal to 3 in the first die, and the sum of the two die is going to give you a number that is greater than or equal to 7, divided by the probability of F, which is the probability of getting a number that is greater than or equal to 3 in the first die. Okay, so we're going to calculate this and see what we get. So let's calculate P of F. So for P of F, again, the explanation is that we want to find the probability of getting a number that is greater than or equal to 3 in the first die. So the probability of F is equal to the cardinality of F divided by the cardinality of S. For the cardinality of F is going to be the number of desirable outcome, that is getting a number is greater than or equal to 3 in the first die. And the cardinality of S is the number of total possible outcomes. So here you have two dice, die 1 and die 2. For die 1, you want to get a number that is greater than or equal to 3. So there are 4 different choices, that is 3, 4, 5, and 6. Now for the second die, we don't care about the outcome of the second die for this calculations of P of F. So there are 6 different choices for the second die. That is 1, 2, 3, 4, 5, and 6. So the number of desirable outcomes is going to be 4 times 6. Now again, you have two dice. And for the number of total possible outcomes, for the first die, there are 6 choices. And for the second dice, you also have 6 choices. So altogether, you have 6 times 6 choices. And you can cancel out the 6, and you're left with 4 over 6, or 2 over 3 for the answer, or for the probability of F. Now, you're going to calculate the probability of E and F. Well, this is the probability of getting a number greater than or equal to 3 in the first die, and the sum of the two dice is greater than or equal to 7. And the formula is going to be P of E intersect with F equal to the cardinality of E and F divided by the cardinality of S. So again, in this case, the cardinality of E intersect with F tell you the number of desirable outcome. In this case is to get a number that's greater than or equal to 3 in the first die, and the sum of the two die is going to be greater than or equal to 7. And the cardinality of S, which is the number of the total possible outcomes. So remember, you have two dies. So in the first die, this is the second die, and you want to know the number of outcomes. So in the first die, you want a number that is greater than or equal to 3. And at the same time, the sum of the two die is going to be greater than or equal to 7. So the first die, if the first die is 3, the second die has to be either 4, 5, or 6. So there are 3 possible outcomes because 4 plus 3 equal to 7, 5 plus 3 equal to 8, which is greater than 7, and 6 plus 3, which is greater than 7 as well. So there are 3 possible outcomes. And this 3 is the number of choices on the second die. So in the case the number on the first die is 4, then on the second die, you have to get 3, 4, 5, and 6 because you want the sum to be greater than or equal to 7. So 4 plus 3 equal to 7, 4 plus 4 is equal to 8 greater than 7, so on and so forth. Therefore, there are 4 different choices in this case, or 4 different outcomes in this case. And the 4 is coming from this 1, 2, 3, 4. Similarly, we're going to go to 5. When the first die give you number 5, then the choices for the second die should be 2, 3, 4, 5, and 6. There are 5 different choices, and they're coming from these choices. So 1, 2, 3, 4, 5. And for the last case, the first die give you a number 6. Then on the second die, it has to be either 1, 2, 3, 4, 5, or 6. So there are 6 different outcomes for the last case. So in total, the number of desirable outcome is going to be 3 plus 4 plus 5 plus 6, and this is going to be equal to 18. So the numerator is going to be 18, and the denominator is going to be the total number of possible outcomes is 6 times 6, because the first die there are 6 different choices, and on the second die is also 6 different choices. Therefore, the number of total possible outcomes is going to be 6 times 6 equal to 36. So you get 18 divided by 36. Now you're going to put everything together. That is, you're going to calculate the probability of E given F, which is equal to the probability of E intersects with F divided by the probability of F. So the probability of E given F equal to the probability of E intersect with F divided by the probability of F. And the probability of E intersect with F is 18 over 36 divided by the probability of F, which is 24 over 36. I'm going to take the reciprocal again. You have 18 over 36 times 36 over 24. And the answer is 18 over 24. And if you simplify this further, you're going to get 3 over 4. So far we see the calculations of conditional probability based on the following formula. That is, the probability of A given B is equal to the probability of A and B divided by the probability of B. And in the calculations, you see that we always try to calculate the probability based on the cardinality. And so for the numerator, you have the probability of A and B is going to be the cardinality of A and B divided by the cardinality of S. And the probability of B is going to be equal to the cardinality of B divided by the cardinality of S. And you see that when you divide a fraction, you can multiply by the reciprocal, and you get the cardinality of A and B over S times the cardinality of S divided by the cardinality of B. And you can cancel out the cardinality of S and arrive as an alternative formula for the probability of A given B. That is going to be the cardinality of A and B divided by the cardinality of B. You see this derivations in the last video already, but in this video, because we have worked on this few example, and you see that you can skip the step of finding the cardinality of S altogether and just need to find the cardinality of A and B and the cardinality of B, and you can get the answer for the probability of A given B. But certainly, however, in general, in finding the probability, is good to calculate the however, in general, it's good to calculate the cardinality of the sample space as well, because by definitions you need that information. But in calculating the conditional probability, you can skip that step. So that's why I want to bring this up again in this video. Now we're going to move on to another example where we have a table of data instead of just word problem. So in this example, you have a table of information telling you the number of survey subjects who have received and not received a speeding ticket in the last year and the color of their car. And using the information provided in the table, we want to calculate the probability of certain scenario. So in this table, you have the following information. That is, there are 15 people who get speeding tickets from last year, and their car is the red car. And there are 135 people who get no speeding tickets, and their car is red. In addition to that, there are 45 people who get speeding ticket, but their car is not red. And there is 470 people who get no speeding ticket, and their car is not red. And at the end of this column, you have the total number of speeding tickets. In this column, you have the total number of no speeding tickets. For this row, the entry is 150 is the total number of the red cards. And this entry is the total number of not red cards. And this number 665 is going to be the total number of people who done the survey. So we're going to find the probability of some certain scenario, but before I do that, I want you to calculate the information that eventually you're going to use anyway. That is, what is the cardinality of certain outcomes in this scenario. That is, if you let the set A to be a speeding ticket, the set B to be a no speeding ticket, red car is the set C, and not red car is the set D. Then you can see that the cardinality of A, or the number of speeding tickets, is going to be equal to 60. So this is equal to the cardinality of A. Then the cardinality of B, or the number of no speeding tickets, is going to be equal to the cardinality of B, and that is 105. Now for the case of red car, the total number of red cars is going to be 150. So that is equal to cardinality of C. And there are 515 cars that are not red. Therefore, the cardinality of D is equal to 515. In addition to that, the value 15 here means that this is the number of people who get speeding ticket and their car is red. So this is equal to the cardinality of A and C. Similarly, this case is the cardinality of A and D. This one is the cardinality of B and C. And this is the cardinality of B and D. So now the first questions of this problem I want to ask is that, can you find the probability that a randomly chosen person has a speeding ticket given they have a red car? So here we already defined that the one who gets speeding ticket is going to be in the set A. So for speeding ticket, this is going to be the event A, and having a red car is going to be the event C. So what you try to do is to try to find the probability of A given C. Therefore, this is equal to the probability of A and C divided by the probability of C. But you can use the alternative formula, that is, the probability of A given C is equal to the cardinality of A and C divided by the cardinality of C. And the cardinality of A and C is already given, in this case, equal to 15. And the cardinality of C in this case also given, that is equal to 150. Therefore, the result is going to be 1 over 10, or this is equal to 0.1. So there are 10% chance that a randomly chosen person has a speeding ticket given they have a red car. Now for problem B, I want to find the probability that a randomly chosen person has a red card given that they have a speeding ticket. So this is kind of the reverse information that we want to know. So the event of having a speeding ticket again is A, and the event of having a red card is going to be C. Therefore, the probability of C given A is equal to the probability of C and A divided by the probability of A. So the probability of C and A is going to be the same as the probability of A and C, and therefore you can just switch them. So you can switch them around. Now you can use the alternative formula to calculate this probability. That is the cardinality of A and C divided by the cardinality of A. Given that the cardinality of A and C is equal to 15, and the cardinality of A is right here is equal to 60. If you use a calculator, you're going to get 0.25 for the answer. That means that there is a 25% chance that a randomly chosen person has a red card given that they have a speeding ticket. Now, I'm going to move on to another example, and it's going to be very similar to what we are doing right here, but in terms of the machine learning that you may encounter in reality. So in this example, you have the following data. So you have something called the photo classified data set, and this represents a sample of 1,822 photos from a photo sharing website. And you're working on this project and you want to know whether or not the photo is about fashions or not. So each photo gets two classifications. The first type is called the machine learning classifications, and it gives a classification from a machine learning system, and they give two answers, right? So they predict that this photo is about fashions, and another prediction is that this photo is not about fashions. And the second classification is actually from you. You know exactly the type of photos that you have. That means for each of these 1,822 photos, you know exactly which one is about fashion, which one is not about fashions. And you write down all of these values into the following table. And you see that there are 197 photos that is predicted as fashions by machine learning model and turn out to be actually about fashions. There are, of course, 22 photos that are predicted by the machine learning system, but turn out they are not about fashions. There are 112 photos that classified to be not about fashion by the machine learning system, but turn out to be about fashions. And there are 1,491 photos which are predicted by the machine to be not about fashion and turn out they are actually not about fashions. So that's the information that you get, and you're going to use these information to calculate the probability of certain scenario. Similar to the last example, I'm going to call a photo that is actually about fashions to be the event A, and not fashions to be event B, predicted by the machine learning to be fashions event C, and predicted by the machine not about fashions as D. So the cardinality of A is going to be equal to 309. The cardinality of B is equal to 1,513. The cardinality of C is going to be equal to 219, and the cardinality of D is equal to 1,603. In addition to that, you have this value of 197. That is, there are 197 photos that predicted by the machine learning system to be fashions and turn out they actually about fashions. So this is equal to the cardinality of A intersect with C. This is A intersect with D, meaning that there are 112 photos where the machine predicts them to be not about fashion but turn out they are about fashions. And there are 22 photos for the cardinality of B intersect with C, and there's going to be 1,491 photos in the case of the cardinality of B intersect with D. And the value of 1,822 is going to be equal to the cardinality of S, so that's going to be the sample space. So you can write down the information that is A is going to be the photo that is actually about fashions. B is the event where the photo is actually not about fashions. And C is the event where the photo is predicted to be about fashions. And D is the event where the photo is predicted to be not about fashions. I'm not going to write the question because I want to calculate a lot of information here, but I'm going to give you some explanation for each calculations. So the first calculations I want to do is I want to calculate the probability of A. That is the probability of getting a photo that's turned out to be fashions. So that is equal to the cardinality of A divided by the cardinality of S. For the cardinality of A is 309 divided by 1822. And that is the value for the probability of A. And this is going to be approximately equal to 0.17. So there is 17% chance a photo chosen randomly from the sample size of 1,822 photos is actually about fashions. Now you can do similar calculations for the probability of B, the probability of C, and the probability of D. So the probability of B is equal to the cardinality of B divided by the cardinality of S. And you get 1513 divided by 1822. And this is approximately equal to 0.83. So there is 83% chance of photo chosen randomly from the sample size of 1,822 photo is actually not about fashions. So I want to point out one thing from these two calculations is that the value that you got here, 0.17 and 0.83, if you add them up together, you're going to get that equal to 1 because the total number of photos actually about fashions and the total number of the photo not about fashions add up to 1,822. Therefore, the probability also have to be add up to 1. So now I'm going to move on to calculating the probability of C and the probability of D. So the probability of C is equal to the cardinality of C divided by the cardinality of S. You have 219 divided by 1822. This is approximately equal to 0.12. Or there is 12% chance of photo chosen randomly from a sample size of 1,822 photo is predicted to be about fashions. So the probability of D is going to be equal to the cardinality of D divided by the cardinality of S. The cardinality of D is 1603 divided by 1822, and this is approximately equal to 80.88. Similar to the last two calculations, these two values have to add up to 1 because the total number of photos that's predicted to be fashions and the total number of photos predicted not to be about fashions add up to the sample size. So in this case, you can draw the conclusions that there is 88% chance of photo is predicted to be not about fashions. So now what about the conditional probability? So the conditional probability, let's say, of A given C, that means that you want to find the probability where the photo chosen randomly actually about fashions given that it is predicted to be about fashions. And by the formula, we get that this is equal to the cardinality of A and C divided by the cardinality of C. So the cardinality of A and C we already calculate, and that's turned out to be 197. And the cardinality of C you got already, which is 219. And this turned out to be approximately equal to 90% or 0.90. So there is 90% chance that the photo chosen randomly is actually about fashions, given that it is predicted to be fashions. Now I'm going to give you another calculations and I'm going to end the video. Another calculations I want to do is the probability of B given D. So this is the probability of photo chosen randomly is actually not about fashions, given that it is predicted not to be about fashions. So by the definitions, the probability of B given D is equal to the cardinality of B and D divided by the cardinality of D. The cardinality of B and D is equal to 1491 divided by the cardinality of D, which is 1603. And this is going to be approximately equal to 0.93. That means that there is 93% that a photo chosen randomly is actually not about fashions, given that it is predicted to be not about fashions. So that's it for this video in terms of example related to conditional probability.